G'day and welcome to Crystal Clear Mathematics, where it is easier than you think. I've recently evaluated a number of integrals using t-Formulae, and perhaps you may well ask what a t-formula is. One of my subscribers certainly did so, and this video and the two following videos are an answer to my subscriber's request. So these videos are for you, Kristen, and anyone else who wants to know. Essentially, there are three t-formulae, and they're formulae that allow us to convert a trigonometric expression into, if you like, a fraction based on polynomials. It allows us, for example, if we're solving a trigonometric equation of a certain class or kind, to convert it into a polynomial, and for certain kinds of equations into a simple quadratic. And presumably you know how to solve quadratics. They're one of the first equations we learn to solve, or equation types. So it's a way of vastly simplifying some trigonometric problems. And in a similar way, t functions can be used to change the format of an integral into a much more readily integratable form. So I'll show you in this video what they are, and in the next two videos you'll see how they can be used to solve certain kinds of equations and what kind, and how they can be used to evaluate certain kinds of integrals. But let's get to this. First I'll explain what they are, and then I'll show you probably about three proofs. At the risk of boring you, I would like you to see all three, and I would like you to adopt one of these proofs and practice it for your homework so that you can reproduce it at will, so you know how they're derived and also what the results are. This is good study. But first of all, let me explain what t-formulae are. It starts by making a substitution and saying, let the letter t replace a tangent of a half angle. That's why they're called t-formulae. Now, if t is worth the tangent of x on 2, it turns out that sine x and cos x and tan x can be written in forms of t. Sine x turns out to be 2t on 1 plus t squared. Cos x turns out to be 1 minus t squared on 1 plus t squared. And tan x turns out to be 2t on 1 minus t squared. So, that in essence is what you learn. So our three trigonometric functions, our three basic trig functions, can be converted into fractions which have quadratics or polynomials in numerator and denominator. Right, a simple linear function and a quadratic. In the context of putting these inside integrals or within certain simple trig equations, we're able to convert trigonometric expressions into polynomials or fractions involving polynomials, which vastly simplifies the work we're going to do. This is a very, very powerful technique. So, what's our first method for getting these? Well, the first method is not to use any diagram at all, but simply to use our understanding of what we call double angles. So, for example, sine of 2 theta, you should know, if you don't already, then you just probably haven't got to that point in school yet, and I will be creating a later video explaining this anyway. But sine 2 theta is 2 sine theta cos theta. The cosine of 2 theta is cos squared theta minus sine squared theta. And tan of 2 theta is 2 tan theta over 1 minus tan squared theta. Now I hope you see in this case at least a remarkable similarity between these two equations. So I might even start with this one. if we replace 2 theta with x, so if 2 theta equals x, I might be off the top of the board there, so I'll just lower that down. If 2 theta equals x, then it means that theta is going to be x on 2. I think you agree with that. If I divide both sides of that equation by 2. And making these replacements in here, we would simply get the tangent of, instead of 2 theta, we write x. And over on this side, we will write 2, and instead of tan theta, we would now have tan of x on 2 over 1 minus tan squared. And instead of theta, I have x on 2. And remember our first definition, or our first, we'll call it a definition, is that the letter t would represent tan x on 2. So this would represent 2 times t, 2 times tan x on 2, over 1 minus tan x on 2 squared, which is 1 minus t squared. So that's where this equation comes from. An identity, if you like, but we'll just call it the t-formula. So that's the tangent. How about the sine? Well, I hope you can see. Again, if I replace the 2 theta with x, I get sine x. And if I replace the thetas with x on 2, I get 2 sine x on 2 cos x on 2. Now, I don't have a ready definition for those, but I do have a definition for tangent. And I know that sine over cosine, sine x over cos x is tan x. So what I'm going to do is I'm going to multiply this by cos x on 2 and divide it by cos x on 2. And I get 2. This here is worth tan of x on 2, the tangent of x on 2. And here I've got cos squared x on 2. Now I'm running out of space. This is a problem with having small whiteboards. But here I have cos squared x on 2. I'll write it in. I think I'm going to have to play some games and rub this out. So let's see how we go here. It's a bit grubby. This would be 2 tan x on 2 times, now cosine is 1 over sec squared x on 2. Because secant and cosine are reciprocal ratios. And we have another identity that says that secant squared is 1 plus tan squared. So replace the secant squared x on 2 with 1 plus tan squared x on 2. And now you can see that this will be 2 times t, because we've now got everything in terms of tan x on 2, 2t over 1 plus t squared. These are sine x. Sine x has been transformed into 2t over 1 plus t squared. And it would do well, if this is your adopted method, to practice deriving these expressions from these functions. Now I haven't dealt with cosine yet, so I think I might just stop the video and clean this properly. I'm suffering my constant battle against space on the whiteboard. So, to find cos x, we remember that cos of 2 theta is cos squared theta minus sine squared theta. Which, I was just hesitating about which of two directions to go. I'll substitute immediately. if 2 theta equals x, we've made that substitution, and if theta equals x on 2, this becomes cos squared x on 2 minus sine squared x on 2. Now neither of these are in the form tan x on 2. So can we create tangent functions? Well, we could. We could, for example, divide all of this by cos squared x on 2 and multiply by cos squared x on 2. So let's do that and divide this by cos squared x on 2 and this by cos squared x on 2. So what do we get? Cos squared x on 2 divided by cos squared x on 2 is 1 minus sine squared x on 2 over cos squared x on 2. Since we know that sine x over cos x is tan x, this is tan squared x on 2. And the cosine, I'll put this in parentheses, or put it in brackets actually. And cosine I'm going to write as 1 over secant. And you can see that this is 1 minus tan squared x on 2 over, and secant squared again using that identity, the trig identity, is the same as 1 plus tan squared x on 2. And since we know that tan x on 2 is t, we've managed to get this in the form of 1 minus t squared over 1 plus t squared. And there's our cosine. Cosine of x converted into this form, given that definition. That's our first way of deriving, using our 3 double angle formulae that I showed you, working through tangent, sine and cosine to derive. If you like that, please practice it. I'm going to erase this now and show you the first of 2 methods using a simple diagram. So let's look at that. Okay, the first of the 2 methods using a diagram uses a diagram of a triangle with an angle of x on 2, which sort of makes sense, doesn't it? And if we know that the tangent of x on 2 is t, and tangent is opposite over adjacent, then we could write t and 1. And if I use Pythagoras' theorem on this triangle, then this length here will be the square root of that squared plus that squared, or that plus that. So I'll write 1 plus t squared. So we're going to use this triangle to derive these. Now, sine of x is sine of 2 lots of x on 2. That sort of makes sense. 2 lots of half x, the 2's divide out, we just get sine x. But this means we can use our double angle formula, which means sine of 2 times this is 2 sine x on 2 times cos x on 2. But instead of having to go through a long process of rearranging to get tangents, we can now read these ratios directly from the triangle. Sine of x on 2, there's x on 2, the sine is opposite over hypotenuse, t over root 1 plus t squared. And the cosine of x on 2 is adjacent on hypotenuse, so it's 1 over root 1 plus t squared. And we get 2 times t times 1 is just 2t on the top. And on the bottom, root 1 plus t squared times root of 1 plus t squared gives us 1 plus t squared. That's a slightly faster derivation, and some students very much like that. They like the pictorial simplicity of it. So there it is, that's the sine value. Now I'm going to erase this and we'll deal with cosine. Let's have a go. the cosine of x will be the cosine of 2 lots of x on 2. And using our double angle formula for cos of 2 theta, we get cos squared x on 2 minus sine squared x on 2. And again, referring now to our triangle, the cosine of x on 2 is 1 over this, so I get 1 over square root of 1 plus t squared, all squared, minus sine squared x on 2. Now sine x on 2 is an opposite over hypotenuse, so it'll be t over 1 plus t squared, square root, and I'm squaring this as well, because it's sine squared. Now of course, the square of the root, or the radical, is just going to be 1 plus t squared. And 1 squared is 1. And over here, we have the square of this radical, which gives us 1 plus t squared. And on the top we have t squared. And you can see, putting them together, since they have the same denominator, you get 1 minus t squared over 1 plus t squared. There's our second result. And our third result will come directly from this as well. I'll get rid of this and we'll do it. I'm a great believer in being able to, or I'll rephrase this, I'm a great believer in setting part of your study time aside to practice deriving the various formulae that you require in order to answer questions in your mathematics papers. I don't think it's good just memorising a formula. I think it's good for you to know where it comes from. So being able to derive or generate it is important. And we're going to do this now with tan x, and I think you can see where this is going. Tan of x is going to be tan of 2 lots of x on 2. And by doing this, it now means we can use our double angle formula. And tan of 2 theta is 2 tan, whatever the angle is, over 1 minus tan squared, whatever the angle is. And this is very quick because already we have tangents and we know that tan x on 2 is t. So we have 2 times t, because tan x on 2 is worth t, over 1 minus t squared. So that derived very, very quickly indeed. That, based on this triangle here, that is the second of the 3 methods that I wanted to share. I know I'm being a little tedious in this, but let's call it thorough. So we're now going to look at yet another diagram, another triangle, that might prove useful to you. Now this last method works from the tangent ratio itself, so I'm going to actually derive the first of the 3 formulae immediately and then draw the triangle. So here's the third method. We start with tan x, which is tan of 2 lots of x on 2, which you now know is 2 tan x on 2 divided by 1 minus tan squared x on 2 equals 2t on 1 minus t squared. You should get quite fast at deriving that. Now, having got that far, and we had derived that before, we draw a triangle not with angle x on 2, but with angle x. Now here we have tan of x, which you remember is opposite over adjacent. Tan of x is this. So if I write the 2t opposite the angle, and the 1 minus t squared adjacent to the angle, and use Pythagoras' theorem, I get the square root of this squared plus this squared, which interestingly enough turns out to be 1 plus t squared. I won't go through it, it's fairly simple work. Yes, I won't go there, it's tempting but I won't. So just use Pythagoras' theorem. This squared plus this squared take the square root and you'll end up with that. By the way, if you're wanting to generate Pythagorean triads, this is one method for doing it. Just choosing values of t. You can use the absolute value of this, and yeah, I hope you know what a Pythagorean triad is. Triangles like 3, 4, 5, 5, 12, 13, 8, 15, 17, 7, 24, 25, 11, 40, 41, 9, 60, 61 and so forth. There are a whole series of them, and they can be generated using patterns similar to these. But that's getting me sidetracked as well. Using this, we can find sine and cosine. Cos of x, for example, the cosine of x will be adjacent on hypotenuse, and sine of x will be opposite on hypotenuse. And you can see that I did them upside down or in reverse order. The cos x is that, and sine x is that. As you can see, by suffering a little bit of pain to start with and then setting up a quite nice little triangle, the results fall out very, very quickly indeed. Now, different students prefer different methods. I've shown you 3 of them, but in every single case, the result is given this. These are the 3 t-Formulae that we derive. And these are the 3 that you must know in order to simplify trig equations and to evaluate trigonometric integrals. And they're going to be the subjects of my next 2 videos. I hope you found that useful. I hope you in particular, Kristen, have found this to be an answer for what you needed. In some ways you're probably still a bit in the dark because you don't know how they're used. But suffice to say, we can convert trigonometric functions into expressions based on polynomials, which gives us a tremendous advantage in solving problems. So, without further ado, we'll finish this video and I'll see you in the next 2. And I thank you for watching.